12.2 Volumes of Prisms and Cylinders. Essential question: can I find volumes of prisms and cylinders? Can I find surface areas and volumes of similar solids? The volume of a solid is the number of cubic units contained in its interior. Cavalieri discovered that if two solids have the same height and the same cross-sectional area at every level, then they have the same volume. For example, a deck of cards has the same volume whether it's standing up straight or whether it's twisted, because it has the same height and the same cross-section. Same with the coins. The coins standing straight up or tilting, as long as they have the same height and the same cross-section, have the same volume. Volume of a prism. The volume of a prism is equal to the area of the base times the height. In junior high, we took a look at the area of the base, which told us our first layer, and then we times it by how many layers that we had. In our course, the bottom layer isn't always a rectangle, so that's why we say area of the base. We don't use the length times width times height that you learned in junior high. For example, this problem, the area of the base is a triangle. It's a right triangle. So we go ahead and we use our triangle shape and we fill in for the base, which is 3, and the height is 4, or vice versa. So the area of the base will be 1/2 times 3 times 4, and the number of layers, or how tall the prism is sitting, is 2. We can do a little reducing. The answer will be 12, and in this case it's 12 centimeters cubed. That's how many cubic units are in this prism. In this shape, the area of the base is actually a trapezoid, and so the height of the trapezoid is 3. The area, base lengths of the trapezoid are 6 and 14. So the area of the base is going to be 1/2 times 3 times 20, and the number of layers on here, or the height of the prism, is actually 5. Do a little reducing, and then the answer is 150. This is 150, and let me erase that decimal. So it's 150, and this will be cubic centimeters. The volume of a cylinder is very similar to that of a prism. In fact, it's easier because the shape of the base doesn't change. It's always a circle. So a lot of us write pi r squared instead of the big B. In this particular problem, the area of the base, again, is a circle. So this will be pi 9 squared. So when we write it into our volume formula, this will be pi times 81. And the number of layers, how tall it is 6. And when we multiply this, we're going to get 486 pi, and the units is cubic feet. In this problem, again, the base is a circle, so we're going to write 4 here. So this will be pi times 16, and again, the height of the prism is 7. And when we multiply it, we'll get 112 pi, and this is cubic centimeters. Let's take a look at being given the volume and being asked to find the height. So it's a backwards problem. Again, the shape of the base is a rectangle. It's 6 by 4, so the area of the base is 6 times 4. We don't know the height, but we do know the volume is 72. And when we solve, we're going to get 3, and we'll label it feet. A little bit more complex problem in that we have to find the volume of a prism and then subtract some area, some volume, and the volume will be smaller prisms, 2 smaller prisms. So the volume of the block is actually the volume of the large prism minus 2 times the volume of the small prism. So here are the dimensions of the large prism, and so what we're going to do is we're going to multiply the area of the base, which is 1.31 times 0.66. That's going to be the area of the base, times the height, 0.66, minus 2, and the area of the base will be these two numbers, which come from here. These two numbers right here make the dimensions of the base, which is 0.39 times 0.33, and then the height of the hole will be 0.66. And if we put this in the calculator, this is the answer we're going to get. Let me remind you of something we learned in 8.2, the areas of similar polygons. When polygons are similar, they have a scale factor, and the ratio of the areas will be the scale factor squared. We're going to have to keep this in mind on this kind of problem. Solids can be similar as well, and when solids are similar, let's compare their areas. So this SA stands for surface area. So this cube is made up of 6 squares. Every square is 256. 6 times 256 is 1,536. This cube is, each side is 16, times it by 6, that would be 96. If we compare the two surface areas, we're going to find that it's a 16:1 ratio. Now the ratio of the two edges are going to be 4:1. Notice 4:1, 16:1. So if I square the scale factor, that is the ratio of the areas, which is what happened in Chapter 8 as well. Now let's take a look at volumes. The volume is the area of the base times the height. Remember, the base is going to be a square for a cube. So this is going to be 4,096. The volume of the small cube will be 64. If we compare the two volumes, it'll be 64:1. Remember that the ratio of the two sides is 4:1. So 64:1 and 4:1, notice that instead of squaring like we did with areas, we're actually cubing. And that leads us to this key idea. And the key idea is when we have similar solids, and similar solids are solids that have corresponding linear measures such as heights and ratios that have a scale factor. Now, the ratio of the surface areas will be the ratio of the scale factor, or the ratio of the edges, squared. When you want to compare the two volumes, you're going to be taking the scale factor cubed. Let's take a look at this problem. We have these two cylinders that are similar. So the ratio of the small radius to the large radius is 1:2. If I want to compare the two surface areas, I know I will take the scale factor and I'll square it. The question is asking for the surface area of the large. We don't know what the large one is, but we do know the surface area of the smaller. So we'll write 48 pi for the smaller. We don't know the surface area of the larger one, so I'll just say surface area here. And we do know that the scale factor is 1/2. I want to square it. That's going to be 1/4. And when I cross multiply, this surface area that I'm looking for is going to be 192 pi, and surface area here is centimeters squared. And so that will be our answer for the surface area of the large. It'll be 192 pi. We're also looking for the volume of the large. And we're going to run across the same proportion. And we do know the volume of the small, which is 45 pi. We're looking for the volume of the large. I'll just call it V. And we're going to take the scale factor, which is the ratio of the radii, and we're going to cube it, 1/8. And so when we cross multiply, the volume will be 360 pi, and we're going to label that cubic centimeters. Okay, I'd like you to stop the screencast and see if you can do something similar to what I just did. And here's the answer.